So yes, what is TOC? If we see in formal definition, what is TOC? TOC is mathematical study of computing machines and its capabilities. Mathematical study of computing machines. Yes, and its capabilities. This is what TOC is about. Next, if we talk about formal languages, TOC is all about thinking, logical thing. Formal language, if we talk about formal languages, first thing we will think about that it is a collection of string. It is collection of string, but the difference is here the meaning of string not important. What's important is the format. If we have that format, we can build a language. Like what will I say? L2, I'll say L1 only. It's we are representing the language as L1, which says a n b n, where n is greater than equal to 1. See, this can include a b, a b b. These all have no meanings in our English world, but yes, the this has meaning in TOC. Likewise, it will go on. Like we will talk about mm, if it is like L2 is equal to a power to the power n, b to the power n, m comma n, certain equal to 1. This is also a formal language which brings up some strings. If L3 is a ww, this is a string copy function and it's also a formal language. Yes, palindrome is also a formal language because we can see there is a format which from which we can establish the strings. Yes. Now if we come to Chomsky. Yes. What does Chomsky say? Chomsky says many things which is very much important to us. This is a whole what is of all the TOC is based about. It's like first will first comes the regular language, which is of type 3 format. Then comes T2 type 2, which has oh, type 2 CFL, type 3 CSL. Sorry for that circle thing. Even you are drawing, draw a little bit nicely, but currently I'm just drawing it. Okay. The second type 2 is CFL, then it's CSL, so context synthesis language, and then comes T0, that is Turing machine. Yes, when we are talking about this, number one, it is regular language. Yes. And which forms regular language? That is finite automata or finite state machine. Yes. So if FSM comes, don't need to bother about anything. Yes, FSM means finite state machine, which will form regular languages. Slowly handwriting is going to be good. Please bear with me until that. T2 is CFL, that is context free language. And it is done by PDA, push down at automata. What is PDA? PDA is so a finite automata with one stack. Yes, the languages which are not found in regular languages, which some of them can be formed in push down automata. We'll discuss this later. T1 falls in the category of CSL, context sensitive language. And it's handled by linear bounded automata. Linear bounded, actually it specifies some space, it, like the strings which will be included in it will be specified. There is a very slight difference between Turing machine and linear bounded automata. Like T0, Turing machine can do all of the things, and it is done by uh, sorry T0 language formed is recursively enumerable language, enumerable. And it's done by Turing machine. Basically, there is very little difference between the linear bounded automata and Turing machine. Like the difference is the size is infinite in case of Turing machines, and linear bounded automata, the stack size is bounded. So yes, nothing much different. And linear bounded automata just for name's sake. Yes. So this is what we need to cover so that the TOC part is completed. It's like so yes. And what is the subset? If you say, then uh, yes. So T3 is a subset of T2, T1, and T0. Yes. By default, all formal language are type 0. That is Turing machine. So yeah, Chomsky. When we talk about expressive power, um, number of languages an automata can be accepting is known as expressive power of that automata. So yes, expressive power. If you have understood what I have said, then it will be easy to know the expressive power of all the automatas. So yes, expressive power. So what I have said that expressive power is number of languages and automata are accepting is known as expressive power of that automata. So according to it, expressive power of finite automata will be 1, because it can accept only one language, and that is regular language. Expressive language, expressive power of PDA. PDA accept two languages. Yes, that is type 2 part, that is regular language and CFL. Likewise, expressive power of uh, linear bounded automata is 3. It is regular language CFL and CSL. And lastly, yes, if you have seen the other three, Turing machine is easy. The expressive power of Turing machine is 4. It is RL, CFL, CSL, and recursively enumerable languages. Yes. So I think you have got what is expressive power. Expressive power is number of languages an automata can be accepting. There is the expressive power of that automata. Likewise, what we are, let me give you a quick recap that according to Chomsky, what it said that we have particularly four languages, and from these four languages we can form many languages, like the first one in which falls under type 3 is regular language, which is made or handled by finite automata or finite state machine. Second, type 2 language is CFL, context free language, which is handled by finite automata. The type 1 is CSL, context sensitive language, which is handled by linear bounded automata. And the type 0, which is recursively enumerable language, which is handled by Turing machine. And Turing machine, you can say, it forms, or it is the default one. The default all formal languages falls under type 0, that is Turing machine. Yes. And what was the basic, which I said? What is TOC? TOC is mathematical study of computing machines and its capabilities. Formal languages mean particularly that it is a collection of strings, but the meaning is not important. What is important is the format. So yeah, these are the examples which I have given. So yeah, if we come about next part, the next part we can, okay, I can show you some. Yes, why these many automatas? Yes, these many automatas are required because from one particular language we cannot form all our desired strings. Yes, so as we'll proceed, you'll need to know that what type of languages we need to form, or we'll see that. So yeah, let's take a question. It says language 1, which says a to the power n is greater than equal to 1. So when n is equal to 1, what are we getting? L1 is equal to a a when n is equal to 2, a when n is equal to 3, a, and it is going on. Yes. So yes, if we form the structures, it will look like something like this. Let me show you. It is state 1, we are passing a, and it is the final state 1 is 2, and a self loop which says the number of a's which we are passing, it will go on. So yeah, we have two states. Next, if we go on with these types. Language 2, which says a to the power n, b to the power n, n is greater than equal to 1. So if we are doing it with finite automata, what is the language saying? Let's just find it out first. A b, if n is equal to 1, then it is a b b, then a b b b, okay, and so on it is going on. So if we are doing with finite state automata, finite automata, sorry, it is like from state 1 we are using a, then we are going to the state a, the a's are going on, then we are going to b, a b, b is going on. But the problem in this structure, if we are doing like this, the problem you can see, if you are able to see that there are, apart from a, a b, double a and double b, there are all others also forming, like a a b, many are forming like this. So we can say that we cannot use finite automata over here, because we cannot form the states which it is wanting. So here comes the format of PDA. PDA says that I'll give you a stack along with the finite automata. So stack plus finite automata, it is what we need currently. So how we'll do it, we'll see now. Yes, I'll draw. We'll represent the start of the string as hash, and we'll start entering A's. Like our string is given as like a b b. At the end of a string, we'll put a dollar sign, which is represent that it is the end of the string. We will enter the number of a's in the string, and then what we'll do, when we see the first b, we'll pop one a. When we'll see the another b, we'll pop another a. And if we see the dollar sign, we'll check whether the stack has hash, that is the stack is empty or not. If it is empty, then yes, the string is accepted, right? And so this language is formed by this PDA. So what did I say? That for every a, push into the stack, for every b, pop a. If the top of the stack is empty, that is hash, then we'll say the string is accepted, otherwise it is rejected. So here comes the use of PDA, which I was saying previously. Okay, now the next question, see if we can do this or not. The why this matter, I think it answers the question why we need these many automatas. If we see L3 is, okay, let me change it, a to the power n, b to the power n, c to the power n, and n is greater than equal to 1. So you can see from here that only that strings will be accepted which has a equal hash number of a's equal to hash number of b's equal to hash number of c's. So yes, how you will do it, I'll not stretch that much, but yes, I'll say that PDA will not be able to solve it. PDA will not be able to solve it. I'll not stretch it. I'll just directly answer it because yes, time is limited. PDA has only one stack, For finding the equality between all the three, we will need at least two stack, that is two stack, and which we don't have in PDA. So we'll go for Turing machine. And Turing machine, so here we, we came to know what is Turing machine. Turing machine is PDA plus one stack, and one PDA plus one stack means two stacks plus one finite automata. So let's see how it is happening. Yeah, let me take the string a b b b c c c. We are entering a, all A's we are pushing it. Okay, then for every b we are popping it. Yes, so we can see that for every way we are popping it. So if this if the first stack is empty, we can see, we will able to see sorry, for every a, for all the a's will enter all the a's in two stacks. Yes, sorry, I had missed it. And we'll pop b's. When we see b, we'll pop a's, and next time when we are seeing c's, we'll pop a from another stack. Yes, c c c will pop it. So from this we can see that both the stacks are empty, and when we both the stacks are empty, that is as hash, we'll say string accepted, or otherwise rejected. Yes, simple concept. So let's see if Turing machine is able to perform a language bigger than this. Mm. So the question is, languages a b to the power n, c to the power n, d to the power n, and n is greater than equal to 1. Turing machine is type 0. All the languages forms under this machine. So whether we can fulfill it by two stacks or not, let's see. We have to prove a is equal to b is equal to c is equal to d. So when we are entering a, for every a we are also entering every b. We are for every a popped, we are entering b in s2. Sorry. When a popped, first b entered, second a popped, second b entered, and third a popped, but B entered. Then when we are popping B, then we are entering C over here. Popping the B, entering C over here. Popping the B, entering C over here. Then again the same. When we are popping C, entering D here. Popping C, entering D here. Popping D. When we can see one of the stacks, this S1 is empty, we can conclude that this is accepted. That is, this language we wanted to make, it's done. We'll make it by these two stacks, that is PT from PTA, sorry PTA, TM. We can form as many as languages as long as the language will be, it will be formed by TM. Hence proved. What we did here, I'm sorry I took much time, but what we did I'll tell you in short. That for every A, first we'll enter all the A's. When one A is popped, one will enter one B. One B is popped, will enter C, and when C is popped, will enter D. When one of the stacks are empty, we'll conclude that yes, the string is accepted. We'll say that doing work with a team, we can say that we are using it like computer programs. Yes, team, like what team words, we'll access that computer programs like this also. So yes, we can come to the main part, which says it says about alphabets, strings, power of an alphabet. Yes, what is an alphabet? What is an alphabet? What is an alphabet? It is a finite non-empty set of symbols. It is a finite non-empty set of symbols. Very much important. It has to be finite and non-empty. When we talk about strings, strings are collection of symbols over a given alphabet. Very much important. It is represented by sigma. From this we can form one length string, two length string, three length string, n length string. Also we can form zero length string, which is very much important. Like we are talking about one length string, we can form A, B, C. We're talking about strings, one length string. When it's about two, it's A, B, B, C, dot dot dot. When about three, A, B, A, C. Likewise, it goes on. But important thing over here is zero length symbol, that is also included. Zero length string, which is represented by epsilon. Epsilon. We generally forget about this, but it is an important part. I can show you some good about this. Epsilon is very much useful to us. Like see, AB length into length 2 and CA, both of are length 2. what will be the length after concatenating a b c a 4 when epsilon ab length is 0 to concatenate it will be ab. It is important. Yes, now let's just come up to power of an alphabet. Power of an alphabet is very important. See, if the string is 8, one line string, two line string, okay, one line string, what will be the a comma b? How many? 2. 2 to the power 1. You can say two line string a b a a b a b b. Yes. How many strings? 2 to the power 2. That is 4. Likewise, when it's about three line string, sigma to the power 3, it is what? It was sigma to the power 1. It was power 2. Sigma to the power 3, 8. Hoga, it will be there. Likewise, if it is about sigma to the power 100, what it is meaning? Power of an alphabet, what do I want to say? It's like when it is two length string, it is entering inside the alphabet, it is entering inside the string two times. Like this is one a comma b, this is one a comma b. First sigma for two less string, first from here something one alphabet, and from second time from here second. So it's like in going inside the string two times. So we comes there comes about the power of alphabet. When we talk about sigma star, it includes all the strings like union. So it will include all languages, all it is called universal set of all strings over the given alphabets, all. Yes. And what about sigma plus? It will include all, only this will be not there, that is epsilon 1 union set of all strings including, remember it, plus has a great significance. It means excluding epsilon. Now come to the language part. What is language? Language is collection of strings over a given alphabet. What is language? Collection of strings over given alphabet. Okay, I'll give you some examples regarding it. Like alphabets are a comma b language AP AAPP AAAPPP. These are all language. What if we write in the other way? It is a bar n p to power n and is greater than equal to 1. Likewise, this is also a language. A bar n b to power n m comma n is greater than equal to 1. These are all subset of sigma star. Universal set subsets. This is also a subset. This is very much important, and this one also. We need to know the significant meaning of this. And last one is sigma AAPP. So yes, what was I was telling about this one? These two are different. L5 means language not empty, only string empty. It is a language. Only string empty. Over here, language is also empty. Remember, if we classify set a language, will have many things to tell. Okay, let me tell you. When it's about set on language, divide into countable and uncountable. Countable, uncountable. It has something. Over here also we can have divisions like countably finite and countably infinite. Like countably finite. The examples: set of all pens, set of all colors. These will take time, but it can be counted. But over here, like set of all natural numbers, it is countably infinite. Set of all regular languages, countably infinite. It comes in exam. This one's important. And this one, set of all real numbers. Yes. After knowing all of these things, we can come to finite automata and regular languages. Yes. What it is. Let's just give a quick recap. From previous tag. Okay, let me give from here. So we discussed why we are needing this many automatas. Because first one finite automata we could form it easily for just a simple language, but when the complexity increased, when the conditions arrived, when there was requirement of storing and comparison, we required push down automata. When secondly, when the difficulty increased, we had to go we were talking about Turing machines, two stacks were required, and when the complexities are increased, we required two stacks, and that were and so. But when we had seen that if there was four a to the power n, b to the power n, c to the power n, Turing machine was enough to do it. One sec. Yes, when the complexity increased, we had seen that yes, TMs were able to rectify or form a language out of it. So yes, TM was a successful, and so it is by default. All the formal languages fall under TMs. When we talk about alphabets, alphabet, finite automata set of symbol, finite non-empty set of symbols. Yes, and when we talk about strings, strings is collection of symbols over a given alphabet. One line string, two line string, three line string, but zero line string epsilon is very much important. Power of an alphabet. Power of an alphabet, as I described, when it is going inside alphabets two times or three times or four times or 100 times, it then we'll say sigma to the power 1, 2 or 100. Now sigma star represents complete language, and sigma plus represent all languages except epsilon. When the language what is language? Language is collection of strings over a given alphabet. Sigma what was the input, that is a and b. Out of this, with all the language are subsets of this sigma star. All language falls under sigma star, remember it. What was this sigma under this one? This one represents language not empty, and string was empty. Yes, language is not empty, but the main string that is empty. Whereas over here, language itself is empty. So yeah. And what was set or language? Set or language is divided into two parts, that is countable or non-countable. Countably finite, we can say that set of scholars, set of all Indians, like these are all countable. But finite it may take certain amount of time. But countably infinite, like it is very much difficult, very much time taking, and so we can say this goes for infinite period. Set of natural numbers, or if we are talking about set of all regular languages, that is countably infinite. What's uncountable? Set of all real numbers. It's like 1 2 1.1 1.0001. These all are real numbers, but it is uncountable. Yes. So yeah, this was part 1. Next, we are going to discuss about finite automata, regular languages. Next part 2 will contain finite automata and regular languages. We will discuss about DFN and NFA. It is this without output, or with output, that's called more a machine or mini machine. So we'll discuss when we can say language is regular. Yes. Yeah. Thank you.